Welcome to the Astrophysics Podcast. Something new about me this year. I had the opportunity to witness the birth of my daughter. Now, I'm not going to bore you by telling you about how happy I am about this. Maybe I can go on about her some other time, but I wanted to bring it up for a reason. Witnessing a birth is an absolutely surreal experience. I mean, it's scary, of course, but it's also just an indescribably crazy thing to see. But that's where we all come from. Which brings me to my next question. Just how was our planet birthed into this universe? What was that formative process like, and how did it shape the way our solar system looks today? For centuries, astronomers, physicists, and philosophers imagined how this might have happened, and at this point, we have pieced together a pretty good picture of how the planets came to be. It all starts off with a giant molecular cloud, a big cloud made of gas and dust, which slowly collapses under its own gravity. As this giant cloud collapses, it fragments into very tiny, dense clumps that eventually will become stars. We call these objects protostars. The remaining material in the cloud continues to fall onto the protostars, but invariably this infalling material will have some small amount of rotation around each protostar, and this rotation becomes amplified more and more as it collapses inward until the gas is spinning so fast around each protostar that it forms into a disk. This disk is an extremely important component of the solar system's evolution. It contains all the material that will eventually form into all the planets, moons, asteroids, and comets that will eventually make up the solar system. And the fact that it all came from this spinning disk is part of the reason our own solar system is so nicely ordered, with all the planets rotating around in the same direction, all nearly aligned in the same 2D plane. The disk is around for the first few million years of the solar system's life until it dissipates. A few million years may seem like a long time, but actually, our own solar system is billions of years old. Nevertheless, the fact that this disk was present in our formative years helped us to grow into the healthy solar system we have today. Which brings me to my guest today. Dr. Merel von Hoff studies these important questions about the formation of solar systems. What sort of environments did the planets form in? And how might these early formative years leave an impact on the system billions of years later? One thing I can say for sure is that the first few months of my daughter's life have left a huge impact on me. I'm Paul Duffel, and this is the Astrophysics Podcast. Now I'm going to hit record, and hopefully everything will work. I haven't done this in a while, actually. I haven't done this basically. Well, Abby and I did one episode since having the baby, but other than that, I haven't done this. So it's I have never ever done this. So well, okay, that's fine. I'm supposed to be in charge nominally. So okay, great. So I guess you're ready to get started. I'm ready to get started. Okay. Welcome to the Astrophysics Podcast. My guest today is Dr. Merel van Hoff. Professor of Physics and Astronomy here at Purdue University. Dr. Van Hoff, welcome. Thank you for joining me on my podcast. Thank you so much for having me. You're welcome. I was. How did I do with your name? Pretty good. Okay. Yeah. No, I know it's hard for non-Dutch speakers. It's really hard. Yeah. How do you say it? Merel van het Hof. Oh, I got it totally wrong. One of these days I'll get it. When I record the intro, I'll listen to that and I'll do much better. So now you have been faculty here for about a year, and yes. So and I first met you when you came to do your job interview here. Yes, that's correct. How was that experience from your perspective? Oh gosh, it was a lot, and I think I don't even remember everything. Yeah. Just being like so nervous and excited to be here that I do remember talking to you like really well. You were like, I think the first thing you said, like, I am not on a committee, like I have no say in this, like we can just like chat. So that was really nice. Oh, good. Yeah, but no, overall, like the interview day was like, I think. In hindsight, it was a lot of fun. I enjoyed giving the talk and like talking to a lot of people. Yeah. Yeah, I felt very welcomed, which is one of the reasons I came. But yeah, I was also very nervous. Yeah, I can't. now me applying for jobs is like, I guess 5 years in the past or something, and I can't remember any of it. It's just like crammed so much in a day.
Yes,
so, yeah.
It's a lot.
But anyway, I was impressed with you right after meeting you, and I thought anyway, I'm very excited to have you on the podcast. I think it'll be a lot of fun. So now we usually start out by asking a little bit about you and how you got to be a scientist. So let's start by asking, where did you grow up?
Yeah, so I'm from the Netherlands. So I grew up there all the way in the north. So Groningen, like the biggest city in the north. Maybe that means something to people. Maybe it doesn't.
That's all right.
The Netherlands is really small. It's smaller than all of Indiana. So, yeah.
Oh, I didn't realize it.
It is really small, yeah.
It's smaller than Indiana.
It is, yes. So... I was born in the city. Then before I was a year old, my parents moved to like a very small village, like a few hundred people small. So I lived there until I finished high school. And then I moved to Leiden for my undergrad, and I stayed there until I had my PhD. And that's like a 3-hour drive, like at most, but for like Dutch people, that is like the other side of the world.
Right. Yes.
So yeah, that's why I'm saying, like, comparing to Indiana, like, and a lot of like Americans, like that's like a very small, very small, like you drive that for dinner almost. I noticed some people do.
It's true.
But yeah, no, especially then, I think at that age, it was a long distance. Like I felt like I was moving far from home. But like little did I know that I would move to the US later on. So, yeah.
So then, so just to give a flavor for our American listeners, that what is like? I mean, can you describe some things that would be different growing up in the Netherlands?
Oh yeah, I think that's a question like a lot of people ask, and I always have to think about it, because I think mostly for me it's like the really small things. Well, just like very on top of my mind, because we just went out for breakfast, right? That's something that we don't do in the Netherlands.
You just don't go out.
You don't go out for breakfast. It's maybe like now, like some of the coffee shops, since that's becoming like popular, they have like some breakfast options.
Yes.
But you just grab something to go with your coffee. I think it's not like here, right? You really go out and you have like all these dishes like brought out, and you take a lot of it home as well. So that's like a very different experience that we don't have in the Netherlands. So yeah, for me personally, it's like a lot of like these small, like little things and distances, like I just said, right? Distances are so different. The Netherlands is so small, and even like driving to the other side of the country, which only takes a few hours, is for a lot of people like feels like a long distance.
That's so funny. We'll regularly have reasons to drive to Indy, and that's an hour trip, right?
Yeah.
So, but we'll take the baby in the car seat. And
yeah, exactly.
It's not the other end of the world. So, can you think of a memory of the first time that you like thought you might want to be interested in science?
I don't even know like when the first time was. I do know that I think I've always been interested, even like probably not even knowing like what science actually was.
Okay.
But I do remember that like from a very young age, I either wanted to be an astronaut or a deep sea diver.
You wanted the suit. You wanted to be in not at one atmosphere.
Maybe that's the common denominator there. Yes, that's true. So I think, and I've always been interested in like the night sky and doing those things. And I also remember my dad did a lot of like bird conservancy kind of things. He was involved in a lot of clubs and organizations, and one of them had like a yearly conference as well. It was like Bird of Praise in the Netherlands. And I don't know how that came to happen, but from like a very young age, like maybe like 5, I just like joined him.
Okay.
And I remember like sitting like in the like big lecture hall, listening to the talks, and remembering like the ones that had the most like images were like the most interesting. And I think that's still the same. Like when I go to a conference, still like the talks that have like the nicest images are still the ones.
That's the ones that stick with you.
So. Yeah. So I think I've been doing like a lot of these things like since.
So your dad
young.
did that for fun, just as a hobby.
His work is also related to like birds and nature from like a local government perspective.
Okay.
But he also did a lot of it like in his free time.
So he worked in the government doing some kind of conservation
Yes,
type.
and looking at regulations for agriculture, how that impacted bird populations. And he has been, I think one of the things that he did for that was like studying how like mouse populations affected like number of different birds of prey. And I remember like joining him like very early in the morning. He would set these live traps in like different types of like crops and like checking how many mice he would like catch, or just like get an idea like how many mice there were every year, because apparently that fluctuates.
Oh.
And I remember like joining him to like do that and like enjoying that a lot. So I think I always had like that interest in science, and like with just the things that my dad had been doing, I just like went along.
But that's so you feel, it sounds like your dad was some influence on you there.
Yeah, I think so, definitely.
And that getting you excited, like I mean, going out, like that seems like some kids would be very bored by that, right? That going out and just checking how the data of how many mice are in this field or something. Do you feel like he was your biggest influence on that in thinking about science, or? I
think so.
Yeah.
And just I think in general, like both my parents always have been like do whatever you want to do, and like pick the direction that you want to do. So they always like let me be very free in that. So I've never been pushed into like, oh, you have to do this or don't do this. So yeah, I've always been able to explore those things.
Yeah. I think that's a pretty common thing, at least from the people I interview. It's very common that say their parents said, you can do whatever you want. So like, oh well, I'll just do this thing. Yeah. I'll just think about space. How's that? But how about at what point do you think are you interested in like astronomy or astrophysics?
I remember always having been like interested in the sky and the planets. So at some point in like, what's for us like primary school, I could do like when other kids were doing like math and like language, like Dutch language, I had like a few hours a week that I could do something separate. And I believe it's from the BBC. They had like a program about the planets in our solar system with like short movies and like a book and like questions. And I did that. Oh. So I know that I was interested then.
Yeah.
But like really knowing that I wanted to do it like professionally, I think came much later. After high school, I didn't know what I wanted to do because I like chemistry, I like biology. I kind of like physics, but not that much. At least the physics that we did in high school, I was like, no, this is not for me.
Really? I think physics was my favorite class in high school, but I also had no idea what I wanted to do. I thought I was going to do sound. I was going to be a sound engineer or something.
Oh, nice.
Like around that time. Yeah. But like, so now I at least have a podcast now. So that takes care of my desire to do audio editing.
Solve that, yeah. Now, I think what saved probably in that sense physics a little bit is that we had in our final year, I think it was called like Project Modern Physics. Mm-hmm. So we had like an additional module where we started like quantum mechanics. And I did enjoy that.
Oh, really?
Yes. Yeah, I know, like weirdly.
No, I mean, it is really interesting, but it's also like very abstract.
It is, yes. So yeah, I don't know what it was, but I think that was the part about physics that I enjoyed the most. Mm-hmm. But then, deciding like what I was going to do going to college. And in the Netherlands, you really have to pick your major from day one.
Right.
So it's very different from like the American system.
In America, we'll let you screw around as long as you want, as long as you keep paying money. In the Netherlands, we have to like decide like from day one. Yeah.
Although I think it's changing a little bit. There's like some more broader programs for the first year. But at that point, like I really had to like decide, am I going to do like astronomy or am I going to do like something else?
Yeah.
And I think even at the point, I didn't really know like what like astronomy would be. I think at that point I knew it would be a lot of physics. Yeah. And I was like, but is that like, am I going to be like good enough at that? Can I do that? Do I want to do that? Mm-hmm. And then, so I was doing like visiting universities and I found a program. It was called Life Science and Technology. It was a collaboration, it was very new at that point, between Leiden University and a technical university in Delft. and it was aimed at kind of making a connection between engineers and industry and people with more like medical, biological knowledge. So we did like genetics, but also like a lot of biotechnology, and you could also go like more in a technical direction. And they really advertised that as like being a combination, like doing some chemistry, doing some biology, a little bit of physics.
Okay.
And it sounded like, okay, this is like perfect. It like combines everything. Like let's do this. So yeah, that's actually what I started out with my first year. Yeah.
Oh, cool. That's very cool. That's one thing that's nice. That is one thing that I like about astrophysics, is not having to specialize, is you get to work on a little bit of everything.
I did not know that at that point. So,
yeah. I used to ask this question. I'll tell you the question I used to ask, which I would say, how you're or what would I say? When do you feel like you learned how to be a scientist? And everyone would say, oh, that's a good question. And then they'd all answer the same exact thing. They all learned how to be a scientist while they were grad students. So I'm going to change the question and ask, if you were to go back to your his grad student self and who at the beginning of grad school, and give them any advice on how you're progressing to being a scientist. What do you think is the most useful piece of information you can give to them about?
Yeah, that's also a good question. And I think our system, so I have to one thing I have to say, our system in the Netherlands is slightly different from the US system.
Yes.
So I think we do our master's first, and it's very separate from then the PhD program.
Right.
And a master's, in principle, anybody who has the right bachelor degree can automatically go into a master. So when I had my astronomy bachelor, it was natural to do the master's.
The master's is just extending your time in college, basically.
Basically, yeah. So it's 2 years, and for us it meant that we had to do a research project in both years and combine that with taking classes.
Right.
But when that was finished, you had to apply again to a PhD program.
Right.
So for me, that ended up being the same university, but that's not guaranteed. So when I think about my PhD time, was I already did the master's, I already did some research, but I know that for the US system, when you come in grad school, you're more at that master level.
Yes.
I think what helped me a lot is in that program that we were kind of forced to do 2 research projects in 2 very different directions.
Yes.
And actually, what I'm in right now, astrochemistry, planet formation, I only knew that existed because I did the research, and I was forced to look at professors, what are they actually, what is their expertise,
right?
What can we do? That I learned, astrochemistry is actually a thing. I did not know this existed, right? If I had known this out of high school, I might have known exactly what I wanted to do right away.
Right.
So I think that would be my biggest advice. Look what actual research topics there are. What are people actually working on,
right?
And it's not just the things I think you see in class.
That's right, and it's also not necessarily the things you see in the big topics that you see in the newspaper all the time.
Yes.
You don't. I mean, they're obviously related because people do these big research discoveries and stuff. There's a lot of people doing really exciting, interesting research that might be not as flashy for the newspapers. So, and then you really know about those things because they're not.
No, exactly.
People don't talk about them. So, then I always found that interesting. Actually, maybe you have because the fact that in a lot of Europe they do that master's thing, and you have to do. You said 2 research projects in 2 years.
Yes,
that's first. So. I think typically that means that the research projects will be pretty small compared to what you would do in an equivalent here as a grad student.
Yes.
Because you need to be short enough you can do the project quickly. And are they both expected to turn into a paper or?
No, they're not expected to turn into a paper at all.
Okay.
You do write a report at the end.
I see.
I think very few master projects actually turned into a paper unless that person continues to do a PhD in the same group. So my first PhD paper is a continuation of the project that I started.
Right.
The second year of my master's.
Okay.
But otherwise, I think few projects actually like turn
that
into
makes
a paper.
sense, because especially just from the experience of grad students here, like your first research project usually takes a really long time to get from like the starting the project to all the way to publishing a paper. Just writing the paper itself takes more than a year usually.
Yeah, exactly. So. No, I think it's definitely not the expectation, and I think at least when I was there, right, it's a few years ago, it happened really rarely unless somebody continued working on it. And I think even like the paper that I in the end published, it's built on like what I did during that last year of my master's, but I think a lot of like the actual results I did like the beginning of my PhD.
Okay. Maybe you can tell, well, no, maybe I'll ask about that when we get into the actual science. But no, you can, since I thought of it, I'll ask about it now. So what was that project that sort of started you on that? Yeah,
so like just like one sentence, it was trying to find whether N2H plus, the molecule, would be a good tracer of the CO snow line in planet-forming disks.
Okay.
Yeah, I probably need to explain that a little bit.
Yeah.
So when we have environments where planets are forming, we have a temperature gradient, right? Close to the star, it's much warmer than further away from the star. And that means that molecules in the gas at some point will freeze out onto dust grains that are present, right? Very similar as like water, when it gets cold, it will freeze down.
Right. So just to clarify, maybe we'll get back to this again when I get it. But just since we're talking about it, I can't stop now. So you have the planets are forming you have a star that's forming and it has a disk around it, and that environment. There's all kinds of different chemicals, all kinds of different, what you'd call dust grains, but also just elements, and there's all kinds of stuff, molecules. But then, for example, like what you first talked about with the snow line, you have water, water molecules, presumably all throughout the disk. But some of it, very close to the star, will be hot, and it will presumably be in a gaseous phase. It's very, very far away from it. You can form ice.
Yes.
That's
exactly the picture, right? If you were to picture like a mountain with like a snowy mountaintop, right, you'll have that transition where like there's no snow or no ice to like ice. That's exactly the same in like a disk around a young star.
Right.
And we want to know for like not only for water but also other molecules, like where is that transition happening with respect to like where planets are forming.
Okay.
Right? Because otherwise you have bare dust grains or you have icy coated dust grains, and it might give you a very different type of planet. But so I looked at the one for CO, carbon monoxide, which is a very abundant molecule. It's a main carrier of carbon, which we're interesting, right? Our life is carbon-based, so that makes carbon-bearing molecules very interesting. But you cannot observe that snow line directly for like many different reasons. So we were using chemistry to see if we could indirectly trace it. So So this is here. So the general idea is that this concept of a snow line, a place where certain things freeze but other things don't, that it can be very important for how the planets form, and because you need certain solids and things to make planets, presumably. But then so it might be nice to be able to look at a disk and see the snow line, but that's not so easy. You can't just look at a distant disk and sort of just look at it and see it. So it's not like a mountain where you can just look at it and see exactly where the snow line is. Yes.
So you're looking for other tracers.
We're looking for other tracers. Yes. So N2H plus, it's a molecule that we don't have on Earth because it's super reactive.
Yes.
But the densities in disks are so low that it can exist. But it reacts very strongly with CO. So when you have CO in the gas, so in the warm region, all the N2H plus is destroyed. But as soon as your CO freezes out and it's ice, it doesn't react in the gas anymore. And that means that N2H plus can be abundant in the gas. So the simple idea is that you would have like a ring of N2H plus just coming from the outer region of the disk, and no N2H plus in the inner region of the disk.
Okay, and that would be an indicator.
That would be an indicator. And I tested whether this was actually the case or not.
Okay, and that was when you were that was a master's
project. Yes.
Okay, and so what was the result of that?
That it does work, but there are a lot of caveats.
Okay.
So it's not as simple as just looking at the N2H plus ring and saying, okay, the inner edge is the CO snow line. There are chemical but also physical effects that you have to take into account.
Okay.
So I guess
so that's actually kind of exciting as a first project, as you get to like really.
I enjoyed it. I enjoyed it a lot. Yeah.
Cool. And so that actually kind of really got you into the field.
Yes. Because actually at that point I was still thinking I would continue with life sciences.
Oh, really?
Yes. I had I started astronomy in my second year in college, and I kind of like staggered and like mixed and maxed, like put my years together, doing them both. Finished both bachelors and then like still couldn't decide. So did both masters. But I lined up the research project such that like my final year would be like a life science project, because I was still thinking like, okay, this is what I'm going to do like in grad school. This is what I want to do. And then when I was doing like this N2H Plus project, my supervisor, Evine van Dishoek, she was like, well, do you know that there's like this fellowship for PhDs in Leiden where they really look for somebody doing like interdisciplinary research, and your interest in chemistry and astronomy and your life science background might make you like a really good candidate. So I was like, okay, well, that sounds fun. Let's apply. It's probably going to be like a long shot, but let's try. And then, like, to my surprise, I actually got that. And then I was like, oh, wow. But I, like, wrote, like, a research idea that if I were to do, like, astronomy research, it's what I want to do. Am I, like, going to turn that down and, like, go into, like, life sciences? And I think at that point, I started also, like, to know that, like, working in a lab might not have been, like, something that I wanted to do for the rest of my life. And then getting that fellowship. So I think that was, like, the turning point of, like, okay, I have to decide. Let's take this amazing opportunity and like roll with it.
That's cool. So, if you were to do life sciences, what would that research project have looked like?
So my final year, I did something that was also, I think, a little untraditional for like most life science students, because I worked with a professor in computer sciences.
Okay.
And it's actually like a pretty funny story. So he had kind of inherited like a microscope from like a colleague from Scotland, I think.
Okay.
And this is kind of a type of a microscope. It's very similar to like a CT scan, but then you would do like biological samples. So you would image them, the sample would rotate, you take like images while it rotates, and then you have like images from like 360 degrees, and then you would mathematically put that together into a 3D model.
Oh,
that was the idea. And but he had gotten the microscope, and it didn't fully work.
I see.
So my project was like, making some protocols and making sure that we could actually do this, because it was like with fluorescence. So we had to do this in the dark. You had to put it was like zebrafish embryo. So you had to like suspend them in like a gel-like substantion. And then we had to make it like very smooth, that there were no edges. Right. Because otherwise you get like effects that the light bends at the edges of your block that it's in. So I had to like figure out how can we make this like very smooth? What kind of like liquid do we need to like suspend it in, that we have like no diffraction between the gel and the liquid? And very practical things, like how do we actually get that like gel to like stick to the microscope, and not like the glue like dissolve in the liquid that we're using. It's kind of funny. Very different project.
It points out also like that you could be, you said life sciences, but none of the tasks you're doing are that, which is often very common in research, is that you're excited about this thing, but then most of your work that you're doing day to day has nothing to do with life sciences. You're trying to like, reconstruct a 3D model. You're trying to get, think about materials that you're dealing with. And
this was very different. The other project I did was working with like muscle cells in the lab, and I think that's where I realized that a lot of this like work in the lab is just a lot of like repetition and trial and error and keeping your cells alive. And it's really important research, and I'm like super important that people do this, but I felt like maybe this is not for me. But maybe if I hadn't had this fellowship,
you might have decided,
I might have done it, and I might have been like super happy.
You might have been you might have gone on the life sciences podcast and said like I'm glad I didn't do astro, because that just didn't seem like for me.
Exactly. So I think I had so many interests, like whatever I ended up, I would have been happy, and it turned out to be like astronomy and astrochemistry.
So actually, let me ask you then this before we get deeper into the science. So what do you like the most about your job?
I think there are many aspects that I like. I like the actual research, like doing the research, studying the topics that I study. I really enjoy that. But I also enjoy working with students and seeing like them like get enthusiastic about these topics or like science in general. Like both with like working with like students right directly like in my group, but also when I teach like a classroom. There's like having those. I remember really well when I was still in Michigan as a postdoc. I also taught introductory astronomy class, and at some point I explained something, and there was like somebody, like one of the students, he like verbally out loud was like, "Oh wow, I get it." Like I think that's like such a like, it just clicked for him, and like just seeing like those moments, I think I just really enjoy seeing that, getting other people like enthusiastic and like seeing it click.
Okay, good. I normally ask what people dislike about their job, but the answer is usually like grant writing. So I don't know.
I actually don't mind grant writing.
Really?
Yeah.
Oh, good. Well, aren't you going to be the money bags then? So.
Well, I mean.
Okay, I hate it, but but I do a lot of it.
Yeah, we all do a lot of it. Yeah.
Okay, so. We're going to now get more into the type of research that you do. So I usually like to start by asking this question, which is when you meet a new grad student or fellow scientist and they ask you what you work on, what do you tell them?
I tell them that I work on studying the environment in which planets form and trying to understand what the chemical but also the physical conditions are.
Okay, so what are the environments that planets form in?
So we talked about it a little bit already, right? So it's disks around young stars, disks of dust, which start out as really, really tiny sand grains, but then over millions of years grow out to be larger and larger rocks, and in the end, full planets and moons. And also gas that either gets accreted and as atmospheres or like giant planets like Jupiter, or freezes out onto these dust grains as ice, and then also can get incorporated into like Earth-like planets.
Right. So before you have a solar system, you first have basically a star forming and a disk around it. And that disk it basically has all the material that eventually will become these planets.
Yes, exactly.
And the other stuff that's around in our solar system.
Yes.
And so when you said you study the chemical and physical something, properties or environment. I don't know. Yes. So what does that mean? Like,
so I mostly say both because they are connected. Yeah. So for example, the physical conditions are like we talked about it a little bit already. Snow lines, which are due to temperature. Another aspect that's really important is radiation. So either UV, cosmic rays, because that influences the chemistry as well. So like in the simplest case, right, temperature determines what molecules can be in a gas phase and what molecules will be frozen out as ice,
right,
or where that happens.
Right.
So in that sense, is that very important to understand what the chemistry is, and what the chemistry, right, in the end will tell us what type of planet we can form. Okay. And if we take that like even a step further, and we're not there yet, but in the end, right, we want to know like how do we get life? And for that, right, we also want to know what molecules can we already make in the disk or already maybe before, and like what molecules for life do we need to make on a planetary surface. So that's like ultimately also one of the reasons why we are interested in this chemistry already.
And when you say, for example, when you say you work on this, you're an observer.
Yes.
For the most part, so you look at systems that we see are in their young phases where they're still forming the planetary system. So you see the disk around it, and so what was, I don't know, I'm lost my question. But so I guess the question is like, how do you study that? Yes,
it's a good question, and I think it's one of the things that I'm still like surprised about, that we can do that, right? Because we can even see molecules right in front of our face. Right. So how can we see like molecules like hundreds of light years away in space, right? That's and the main reason that we can do that is because in these environments it's so very cold that molecules are only rotating very slowly, and they have different ways that they can rotate. And I compare that like to us, like we can exercise for a little while, but we rather sit on the couch, right, most of the time. So, right, we want to go out of that like excited state to like our resting state.
Okay.
And molecules are the same, right? They can get excited due to temperature or like collisions with other molecules, but they always want to go back to like that relaxed state. And in order to do that, right, you have to get rid of the energy.
Okay.
And that energy is light that we can see.
Okay.
So we're basically seeing molecules like chill out and like getting rid of that excess energy, and we can observe that with telescopes, either on the ground or like in space.
And that basically the way that the light that comes from gives a signature of the structure of that molecule.
Yes, because every molecule has a very specific color of light or frequency of light that it emits. So we can, if we observe a whole range of frequencies, we can basically read that as like a barcode, and that tells us like, oh, we have these and these molecules present.
And so that tells you what the composition is in a disk, I guess.
Yes.
And so, actually, I just thought of a question, which is how big do these molecules get in disks?
Yeah, well, that's one of the questions that we're trying to figure out.
Okay,
yes.
Good. I just thought of that.
Yeah, no, that's a really good question. That's one thing that we want to know. So right now, I think the largest ones that we have seen in disks, maybe up to 8 to 10 atoms, so still really small.
Right.
So yeah, well, as astrochemists, what we call anything more than 6 or more atoms, we call complex.
Okay.
And so I know like any other chemist like laughs at that. There's like methanol, for example, is like what we call the simplest complex molecule.
Right.
And I think for like any other chemist, this is like insanely simple.
Right.
But yeah, in space, that's where we start counting like complexity. And we know in like earlier stages, before the disk forms around a young star, it's a little warmer. Mm-hmm. So you have more molecules in the gas instead of in the ice, and we can only easily see them in the gas. So we see maybe a little bit more complex molecules, but like 10, 12 atoms, I think roughly is the limit that we're seeing in like organic molecules.
But then I guess you said we don't know the answer to how big they get while they're in the disk, I guess. Is that because we don't, basically those are the ones we see or can tell that they're there? So
the thing is like the larger the molecule gets, the rarer it is.
Okay,
right? In the end, we start from atoms. Right? After the Big Bang, stars exploding, right? They create atoms, maybe small molecules.
Right.
So we start out with like maybe something as CO2 atoms, and it has to grow into larger and larger molecules. So it's easy to see that if you need something that has 20 atoms, you need to combine like 10 2-atom molecules already, right? So you'll have 10 times as few larger molecules than like the smaller one.
Right.
So that's one aspect. And also this light that we observe gets spread out over more and more frequencies the more complex the molecule gets. So every individual like stripe in your barcode, so to say, gets fainter and fainter.
Yeah.
And that just makes it technically harder to detect them. So there's fewer and they're harder to detect, and that both adds up to making it harder and harder.
I see. So then we've gotten the ability to observe complexity up to 8-ish atoms. But they're presumably, we I guess theorize that there is certainly going to be more complex atoms out there, but they're rare and we don't know how rare they are. I guess. Okay.
Yes. So that's what we're like, both technology-wise, trying to push. Getting more sensitive telescopes would help. Mm-hmm. But on the other hand, right, I say we, but like the field, making chemical models and trying to predict like what molecules will be the right ones to search for.
Right.
That's to help guide that search a little bit.
Once you get to a high enough complexity, there's like got to be a lot of different molecules you could be looking for.
Exactly.
And so actually even picking which one to look for.
Yes. And then making sure that we have data from the lab that we know, right, this is the frequencies, these are the colors that this molecule actually has, right? Because if we don't know that, then we don't know what we're looking for, right? So it's really interdisciplinary research in general, right? We need the predictions from theory, we need chemists in the lab here to like measure those, what we call spectra, and then we need like the telescopes to observe it. astronomers to interpret it.
Okay, so then why don't I ask what is like sort of your role in that? Like what's an example of like how your day-to-day research and what does that look like?
Yeah, so I am really mostly on the observing part.
Mm-hmm.
So I observe disks, trying to find molecules, trying to see like what different molecules we have. Also how they are like spatially located. Do they have like different locations in the disk where they're most common?
Okay,
yeah,
so it's not just pointing the telescope at this disk
No.
and saying like what are the abundances, but also like pointing it at different parts of the disk and
Yes.
saying do you have is the abundance changing as you get closer to the star or
Yes,
sort of thing?
yes.
Okay, and so I guess you talked about the snow line and stuff. What are you have any sort of good examples of recent results like from that?
Yeah, so we have been studying like these snow lines and the chemical composition. I think like a really interesting result that we had, it was in collaboration with a professor in Leiden, Melissa McClure.
Mm-hmm.
We had that early this summer where we actually found a solar system in the making at like the earliest stages we had seen so far.
Oh, how early is that?
Really,
Or we don't know?
we don't. It's really hard to like age like young stars,
Mm-hmm.
but definitely within like the first probably like 100,000 years.
Okay, wow.
So really, really early. So yeah, I think I compared it once to like really like a toddler, even like younger than a toddler, like really an infant phase.
Right,
because
right.
we had seen like some systems where we see like signs that the dust grains grow to like pebbles or like larger rocks. So that would be maybe like a toddler phase. But now we really saw like the earlier stage, so like an infant solar system.
And what are the challenges in seeing really young systems? Is it just catching them before like in that early stage, or?
One of the hard things is that in the earlier stages, you don't have like a nice young star with a disk around it, right? It's a very ordered system. It's a star, it's a disk, like a pancake, flat thing around it.
Mm-hmm.
But earlier on, there's a lot more material still surrounding the disk. That's kind of obscuring the disk sometimes as well. So you might not even see that there's a disk beneath like all the dust and gas that's like still surrounding the system.
So actually that's sort of like what you said before about getting into a relaxed state, right?
Yes, yes.
The over some time it turns into this nice clean disk around a star and it's easier to observe it.
Yes.
So, okay, so then at these early stages...
There's a lot more going on. That's like, right, the disk is forming, there's other material still surrounding it, falling onto the disk, onto the star. The star is also ejecting like material, so we see outflows, jets.
Yeah.
So yeah, overall there's just like a lot more going on, and it's harder to, like, when you see emission from a molecule, it's harder to determine, okay, what component of the system is it actually coming from?
Yeah. So then this particular system, what was the name of the system? Do you remember?
This was it's Hobbs 315.
Okay.
So it has a not super exciting name.
That's okay.
But
I just wanted to know it.
Hobbs 315.
Okay.
Yeah.
And what was special about this that made it possible to do this?
This was a combination with the James Webb Space Telescope and ALMA, so the Atacama Large Submillimeter Array in Chile.
Mm-hmm.
And we needed both to really see signatures of the beginning of planet formation, which we know from our own solar system.
Right.
Yeah, and we kind of found it a little bit serendipitously. We had the James Webb observations targeted at something completely different. We knew that this source had some signatures that we've seen with an earlier telescope at Spitzer that we see only in around very few young stars. So we knew that this was an interesting object to observe, but we had not anticipated that we would find this result.
So you're saying the beginnings of planet formation. What do you mean by that specific? Like, is there a particular time when you would refer to as the beginning of planet formation, or? That's
a really hard question as well. From the solar system perspective, we can look at meteorites, and we consider them to be like the oldest material in our solar system.
Okay.
So, and in the formation of the solar system, we think the material around the young sun was so hot that all like molecules that might have been present, all dust grains that might have been present, just completely evaporated and atomized. So we have like a very hot atomic gas that's then cooling down and forming the minerals in the dust grains, and like basically forming everything as it slowly cools.
So then those first like rocks that are first forming initially have a very particular composition that is what we see in meteorites.
Yes, and that's what we often in the solar system said, okay, this is like T equals 0. This is our starting point.
This is when this really are starting to form actual material and not just having some molecules.
Yes.
Yeah,
and that process, we had never seen that happening around another young star before. So we didn't know if this was something that was just very specific to our own solar system, or whether this is a general process that happens around all young stars, all planet-forming systems. So this was the first time that we actually saw this very initial step of condensing of minerals around another star.
And it means like you're forcing me to jump around in thought, because I have to think about meteorites, and I have to think about
I know. Yeah.
gaseous disks and dust in disks and chemistry. So it's a lot. You're right. It's very. I mean, I appreciate all of astrophysics is interdisciplinary, but this is like a lot that you have to think about. Yeah. And so then, when you look at these systems, you were saying like. You see, you can see evidence for these things. So how do you see it?
Yeah. So again, like these spectra, the emission from molecules is what we're looking for. Yeah. So in this particular case, we saw initially with James Webb signatures of SiO gas, so silicon monoxide gas, at a temperature of about 500 Kelvin. So that might not mean immediately anything to you. Mm-hmm. But what you need to know is that these silica mineral grains, they only sublimate when the temperature is higher than 1500 Kelvin. Okay. So naturally we would expect all the silicon to be in these grains. So seeing like any form of like silicon in the gas at 500 Kelvin is like weird, because we expected it should be in grains.
Okay.
And that's kind of led us to the hypothesis, well, maybe we're seeing like this remnant of this hot cooling gas, the minerals are forming, and we also saw signs of
yet coalesced.
Not everything.
So there's some stuff that's still that's still in a gaseous phase, but it just hasn't had time.
Yes, we either think it hasn't had time yet, or the balance, like the abundance balance with other elements that go into these crystals is just so that we have like some silicon left. All the iron, magnesium has been used up, went into these minerals, and maybe there's some silicon left.
Right.
So we're trying to like understand that and like seeing how much we have of everything. But yeah, that was basically the signature.
So the idea was to specifically look for silicon oxide, or
the proposal was not meant to look at that, but this was just like this was what we saw. Yes.
Eventually you saw these lines and you said, okay, that's silicon oxide.
Yes.
How do we explain that?
Yes, and then we followed that up with ALMA observations, because we do see silicon in the gas phase and like in these outflows that I mentioned, because there you get like violent shock conditions that you can actually like shock some of the silicon out of the dust grains. So there we see it commonly. And with JWST we didn't have like the spatial resolution. We couldn't see sharp enough to like pinpoint where it was coming from, and with ALMA we could do that.
So actually then maybe we should make a distinction between James Webb, which is always like the one that's in the newspapers now, and ALMA, which we've had for a while. I guess we've had that for about a decade now.
Yes.
This maybe you should explain some of the differences.
Like the obvious main difference is James Webb is in space and ALMA is on the ground.
Yeah.
And the other main difference is that with James Webb we observe infrared light.
Yeah.
And ALMA operates at sub-millimeter wavelengths, so longer wavelengths. So we see very different types of light.
Right.
And they originate in different conditions, So from my research, it's mostly that in the infrared, we see much warmer gas. Okay. So for this, really the innermost region, where it's like maybe a few thousand, like hundreds to thousands of Kelvin. And then with ALMA, we see colder gas. So we see the bulk of the disk, where it's like maybe a few tens of Kelvin.
Okay. Yeah. So if you want to see different parts of the disk or different, either material or either that's at different temperatures and things like that, these different observing facilities are, complementary to
Yes,
each other.
they're very complementary. Yes. And then with ALMA we also can get very high detail, so we can really see structures in the discs.
Oh, right. The resolution.
Yes, the resolution is amazing.
Yeah.
And with JWST we don't have that resolution for discs, so we can not resolve the disc as well as we can do with ALMA. So we can see a little bit more detail with ALMA.
So I normally think, now ALMA is used for a lot of things, but I always think of ALMA as the disc telescope. It's the one that you can, because it's really nice for resolution of discs and good at seeing dust grains and things like that. And so, like, if you Google ALMA images, there's all kinds of great images.
There's all the beautiful discs. Yes.
Yeah. So that was the sort of recent result on I forget the name of the disc. Was it
Hobbs 315?
Hobbs 315.
Yes,
so memorable.
So catchy, right? Yeah.
I don't remember it, but I can edit it so it sounds like I remember that. So that was Hobbs 315. And so generally, you're looking a lot of these young systems that are still in the formation and learning about the process of planet formation. So, and I guess in your time, like, what would you say, like, in terms of like studying disks? It doesn't have to be about your research, but like, what are some of the big changes that you've seen in like how we understand these systems, or that have happened since you were a grad student?
Yeah, I think the main change, like a big change that we've been seeing, is that we now know that like the material in these disks is not smoothly distributed. So it's not a smooth dust disk, but instead we see rings and gaps in the dust. So I think has been like one of the like big changes. And another change that kind of started and drove like my proposal for my PhD research is that we think that planets start forming much earlier when the disk itself is also still forming. So not in these nice, clean protoplanetary disks, but already in this messy, chaotic earlier phase.
So the actual formation of these massive bodies happened, the idea is it happened actually much, much earlier.
Yes.
And then they're kind of just sitting in these environments, waiting for the disk to go away.
Well, I think there's still some formation going on in the nice, neat protoplanetary disk stage. Mm-hmm. But there's different lines of argument and like, evidence show that it probably starts already much earlier. Yeah. And I think, for me, just like thinking about the process, like why would you wait with like growing your dust grains until you like have your nice disk? Like why don't you like start it immediately when the disk is still forming? So I don't think it's like,
I think that's
unexpected.
I do think that's probably a hard question. I think we're still trying to figure out how, like the concept of how does the process of like two dust grains coming together and forming a bigger dust grain, like that is the time scale for that is there's many challenges that we still have there. But I think one thing that we started to realize is that we should not just look at these like neat, like well-formed protoplanetary disks, but we should also like look at like what happens already early on. How large can we grow our dust grains already there? What processes are at play there? Like how is our chemistry affected there, and how does that then like evolve all the way to older stages? It's funny. The other thing you mentioned was that these, we previously described these systems as really nice, smooth distributions of dust. I always find like the history of it works. It's not that we necessarily think that that's how they are, but because our observations aren't good enough, that's just how we model them. Because there's no reason to have a more detailed model than your observations going to. Yeah,
exactly. Yeah. But I think we're seeing more and more, probably unsurprisingly, anything that we study in more and more detail, I think we hardly ever find like that it's easier than we thought. Right?
That's right.
I don't know, like an example.
We've got really good detailed measurements, and it looks, when we went to high resolution, it looks just as smooth as it did.
Yeah, right. So I guess in that sense, you could have predicted that looking at something at high resolution, it's going to make it more complicated. I think that's one of the things that we're finding. And also in the chemistry, that not all molecules are distributed in the same way. It's not like necessarily, so far as we know right now, related to the structure that we see in the dust. So I think those are some of the main changes that we have had in like the last decade, with ALMA coming online, but also now with JWST, we're getting more and more detail about the structure of the disks at different stages.
Okay, great. All right, I have my last question, which is, or whatever, I don't know, penultimate question. Why should we care about astrophysics?
Like from like the science perspective, or like in general?
I asked this question with no context, and everyone answers it differently.
Yeah. So I think the nice thing for me personally about like astrophysics is that it's something that like every one of us has in common, right? We live in the same universe, we live on the same planet. Whatever beliefs you hold, right? We are on the same planet, the same space. So I think it can be something that really connects across differences, and it's something that, right, influences us all. It's something that we can see, right? We can all see the night sky. It's something we can all think about. I think that gives us a sort of beauty that it can be maybe like a common denominator that we all have. And I think, right, where we come from, what our place is in that universe that we can all see, I think is a question that also anybody has asked themselves at some point or in some form. So yeah, I think it is important to study that question as well as like broader astrophysics.
Okay, I agree. I always agree with everybody's answer. Even when they say we shouldn't care. No, I think it's great. So what do you think is the next big sort of thing in your field that you're excited about?
I think the big next thing would be to, right now we've been studying like a few individual disks, but really bringing this into like larger number statistics, so to say, really getting more disks and see, okay, what structures, like what molecules, like what is really common among them all, and what are individual differences, and how much does that matter in like the planetary system that we're forming. So
I know you feel like we're moving in that direction, like we're
slowly. I would say like too slow, but that's probably because I'm in the field. I'm writing the telescope proposals that keep getting rejected. So like I think
she's trying to look at too many disks.
Well, it's either like the comments are like it's either too many or it's too few. So
yes.
But I know they are like time intense. So you need a lot of time on a telescope to start doing these detailed studies of a large number of disks. So
and you'll more likely get a newspaper article if you get a really nice image of one disk, right? And you can show it off.
Yeah, exactly.
But if you want to do like science, it can often be much more powerful if you can do statistics and say like this is how things generally happen.
Yes, exactly. So but I think like slowly as a field we're trying to do that, but we have to work with the telescopes that we have and the time that is available.
All right, great. Well, thank you, Dr. Van Hoff, for joining us. I had a lot of fun talking science with you, and I hope you'll join me again sometime.
Yeah, thank you for having me. I had a lot of fun too.
Well, that was probably the most interdisciplinary episode we've ever done, and I know we've only scratched the surface of what we can learn about the formation of planetary systems. So thank you again to Dr. Van Hoff, and thank you to our listeners. We will see you next time. The Astrophysics Podcast is currently unfunded, but always ad-free. The music you hear on the Astrophysics Podcast was written and recorded by Britton Ashford from her album Trotter. All songs are used with permission from the artist and producer. Look up Britton Ashford if you enjoyed the music. This podcast is produced in beautiful Lafayette, Indiana by me, Paul Duffel, Professor of Physics and Astronomy at Purdue University.